the first thing that we are going to see is the overview of the Etabs model that we have selected for the workshop. So since our focus was only on the design part, that's why we decided to select a very basic Etabs model, which does not have any complication, so that you can understand the analysis results quite easily. That is why we have selected a very basic Etabs model. So this is the plan view of that model. As you can see, there are four grids in the X direction, spacing at 5-meter uniform distance. Similarly, there are 4 grids in the Y direction, again spacing at 5-meter uniform distance. So this is our basic plan view that you can also create in Etabs easily. Then we have beams, columns, and shear walls. Shear walls, just for the sake of simplicity, are located at the 4 corners of the building. Now, going ahead about the heights and the number of floors that we are considering, since we are also going ahead with the ductile design of beam and column, that is why we decided to intentionally select a parking plus 12-story building, so that we will get some, ductile analysis, the earthquake analysis results. That is why we selected a parking plus 12-story building. Again, the story heights are kept uniform, 3.6 meter, no complication here also. So as you can see in the elevation, base to story 1 basically represents our building from foundation up to the ground level, and then we have 14 stories above, which basically represents a 13 stories above, sorry, which basically represents a parking plus 12-story building. On the left hand side, we can see the 3D view of the Etabs model. So this is the basic geometry of our Etabs model. I'll once again go to the previous slide. This is the plan view. 4 grids at 5-meter interval, shear walls at 4 corner, and basic beam and column frame inside it. This is the story height and the 3D view. Story height is kept 3.6 uniform, and it is a parking plus 12-story building. Now, about the materials that we have used in the analysis. So being a parking plus 12-story building, we are using concrete grade of M30 and steel grade of Fe 500. The section properties that we are using, all our columns are of the same size, that is 300 by 900 is the column size, all columns of the same size. Beam size is 300 by 600. Again, all beams are of the same size. Slabs are also of the same size, 150 thick slab of M30 grade. Shear walls are also 300 thick, and they are basically spanning from one grid to another. That is why the length of the shear wall, you can see from the view, it is 5 meter. All the shear walls are 300 thick and 5 meter in the length. So this is the brief about the material properties and the section properties that we have used in the model. So all of you can also replicate this model very easily. That is why we kept it simple. Now, coming to the next slide, which is the gravity loads. Now, the loads we have basically categorized into 2 parts. First thing is the gravity load, and second thing is the earthquake load. So gravity loads means our basic dead load and live load. So the gravity loads details are as follows. So the first load is basically the self weight of the structure, whose load type is assigned as dead load, obviously. And since you all are familiar with Etabs, the self weight multiplier is kept 1 for this particular load pattern, so that the self weight of structural members is calculated automatically using Etabs. The next important load is the floor finish, whose type is selected as super dead, and the value assigned, the uniform value is assigned on all the slabs, which is 1.5 kilonewton per meter square. Next load is the false ceiling load, whose type is again super dead, and its value is kept as 0.5 kilonewton per meter square. brick wall whose type is also super dead. The value of the brick wall load is 5.5 kilonewton per meter, and this brick wall load, it is applied on all the beams. Okay, the floor finish and false ceiling load was applied on all the slabs. So this was all about the dead load. The next load is the live load. So we are considering this building as a commercial building, and that is why the live load is kept at 4 kilonewton per meter square. Again, the live load is applied on all the slabs of all the floors. Very simple loading arrangement. And these loads are just assume the standard loads that we take in the industry. So I am not going into the details of it because we want to go to the design part very soon. The next important thing is the load combinations that we have used. So we have used the basic load combinations that are given in IS 1893. So the first combination is 1.5 dead load plus live load, which is basically used for gravity design. And the next combinations are due to the introduction of earthquake load, which are 1.2 dead load plus live load and plus or minus earthquake load. Third combination is 1.5 dead load plus or minus earthquake load. Last combination is 0.9 dead load plus or minus 1.5 earthquake load. So the various combinations that are being generated because of this plus and minus sign are added into the Etabs model. Then the type of diaphragm. Now, all those who have done earthquake analysis in Etabs, we know that in order to perform the earthquake analysis, we have to assign diaphragm to our model. So the type of diaphragm selected was rigid diaphragm. All the supports are being considered as fixed support. And on the right hand side, you can see the snapshot of the load combinations from the Etabs model. So intentionally, we have edited the first combination as 1.5 dead load plus live load. Its name has been edited, whereas the other names are those which are being generated by Etabs by default. There is one more combination which is envelope. So the main purpose of envelope is to combine the results of all the load combinations together so that we will get the worst results out of all the load combinations whenever we want to view them. So that is the load combination of envelope. If anyone does not know that what is an envelope load combination, then they can just search on Google or study Etabs manual and they will get an idea what is envelope load combination. So this was about load combinations. And one more thing, now since we have muted all of you, in case if you have any doubt in whatever we are presenting, we are going to have a half an hour question and answer session at the end. So we will try to resolve all your doubts during that session. So you can just note down whatever doubts you have. So this analysis part, I am just quickly going through. Now, the load pattern, this is the snapshot of the load pattern that we have assigned in Etabs. I have already discussed the loads. You can see them on the screen. First is the self-weight. Type was selected as dead. Its self-weight multiplier is kept as 1. Live load is there, whose type is live. Multiplier is 0 because we don't want Etabs to add self-weight in this particular load pattern. Floor finish is there, brick wall is there, false ceiling is there. And the next two important things are earthquake in X direction and earthquake in Y direction. So considering the IS 1893 2002 code, they have been assigned in the model. And at the left bottom corner, you can see the snapshot of the seismic load pattern, which is assigned for EQX. The direction is considered as X. It is applied from story 1 to story 14. Earthquake load is applied from story 1 to story 14. Response reduction factor is considered as 5 because we are assuming that we will design our beams and columns using IS 13920 ductile detailing code. That's why we are considering R factor as 5. Then Z is taken as 0.16, seismic zone 3. Soil type is considered as medium soil, 2, importance factor 1. And another important thing is the time period. This time period calculation is given in the next slide. Similarly, we have earthquake load in the Y direction. Again, all the parameters are same. We have the same time period in X and Y direction, because if you can recall, our building is a perfect square, 20 meter by 20 meter. So the time period will remain same in the X direction as well as in the Y direction. Now, important thing in this slide is on the left top corner, which is basically the mass source that we assign in Etabs. So all of you know the purpose of this mass source. So basically, IS 1893 allows us to somehow reduce our live load while doing the seismic load calculations. So that command is given to Etabs in the form of mass source. So that is presented in the left top corner. All our multipliers are kept as 1. Only the live load multiplier is kept as 0.25, because our live load is greater than 3 kilonewton per meter square. I am not adding any reference of this here, because that is not exactly the purpose of our workshop today. This is just the details of the model. But you can definitely refer IS 1893 and see that where this clause is given of reduction in the live load. Okay, so these are the details of the equivalent static earthquake parameters that we are using in the model. Time period, as I told you, it is taken as 0.94. So the basic formula for time period calculation is 0.09h under root d. In that, the height of the building is considered as the height above the ground floor, that is 46.8 meter. So it is basically the height of the entire model minus 3.6 meter, which is the height below the ground. So you can refer IS 1893 for how this height is to be calculated. And of course, the dimension in X and Y direction of the building, that is 20 meters. So if you evaluate this formula, 0.09h divided by under root d, then you get a value of 0.94, which is assigned to the model in X direction as well as the Y direction. Rest all the parameters we have already discussed. Just the references of all those parameters are given in the remark table. Response reduction factor 5, it is taken from table 9, clause 7.2.6 of IS 1893-2016. Then Z factor, soil type is selected as medium, importance factor 1. All these references are from IS 1893-2016. So this is the end of our first part, very basic part, that is the overview of our Etabs model. I hope so that all of you have now understood how the Etabs model that we are going to use in this workshop was prepared. It is very basic model with very basic loading parameters. And now we will move on to the second part of our today's session, which is decoding beam design. So as I already told you, we are going to discuss two types of beam. One is the ordinary beam and second is the ductile beam. So let us start straight away with the design of ordinary beam. Now all of you, please pay attention. The actual workshop has now started. So this is the manual calculation of an ordinary beam in Etabs. So what we have done is we have selected one random beam in our entire Etabs model. We have extracted the analysis forces from Etabs itself, obviously, and then using those analysis forces, how Etabs is going to perform the design, and it is going to get the design forces that will be discussed, and how the reinforcement is calculated using these design forces, that will also be discussed. So the beam that we have selected for our study is on story 4, and it is the beam on grid 4, and in between grid B and grid C. So all of you can see it on the screen. The beam is highlighted and the basic BMD of the beam is shown. And on the right hand side, you can see the analysis results of the beam. So now I want to make one thing clear. When we say that we are doing an ordinary beam or an ordinary column, it represents that we don't have earthquake load in our model, just for our simplicity. When I say an ordinary beam or an ordinary column, it means that I am designing my structure for pure gravity load. So you can represent it to the small structures that we design, say some small bungalow or a small row house where we don't want to consider earthquake loads. So that beam we represent here in the workshop as an ordinary beam. So obviously it will be designed only for one load combination, that is 1.5 dead load plus live load, which was also highlighted in the previous slide. This is the first load combination of 1.5 dead load plus live load, which will be used for designing the ordinary beam. So on the right hand side, you can see the analysis results that we have extracted. So it is a beam whose number is B10. It is on story 4. The shear force, that is the maximum shear force in that beam, is 126 kilonewton. Bending moment at the center is 91.22 kilonewton meter, and at the support is 89.15 kilonewton meter. So just for the sake of simplicity, these two bending moments we will round it off to 90 kilonewton per meter, and the shear force we will round it off to 125 kilonewton, just for the sake of simplicity, because that 1 kilonewton per meter or that 1 kilonewton meter or 1 kilonewton is not going to make a big difference. But just to keep the calculation simple, we will round off these bending moment values to 90 kilonewton meter and the shear to 125 kilonewton. So I will just show it to you in the Etabs model once, that how exactly we have extracted these analysis forces. So we have two models, as you can see, one is gravity and one is earthquake. So I'll select the gravity model because we are going to study the design of an ordinary beam. So we are already on the story 4, and this is the beam that we have selected for our study. So I'll just run the analysis and switch on the analysis forces. Yeah. So these are our analysis forces, right? So as you can see, this is our shear force of 126 kilonewton, and this is our bending moment at the support, approximately 90 kilonewton meter. And if we go to the center, or I can just say show maximum, then our bending moment at the center is 91 kilonewton meter, which we will approximate it to 90 kilonewton meter for our understanding. So I have just shown you how we have calculated these, or we have extracted these analysis forces from the model itself. And now I will once again go back to the presentation. So the first part in the design of ordinary beam is the design for flexure. So the maximum bending moment, as we have already seen, at the center was 90 kilonewton meter, and at the support was also 90 kilonewton meter. So these we have extracted from the analysis results of the model. Now, okay, that thing I'll tell you later. The beam size that we have selected is 300 by 600. That is 300 is the width of my beam and 600 is the depth, overall depth 600. Concrete and steel grade are M30 and Fe 500. Now, effective depth of the beam, all of you know the concept of effective depth. So I will not go into the details of that. I'll just tell you the calculation. So basically we are assuming the clear cover to our beam as 20 mm. The stirrup of the beam is of 8 mm and the longitudinal bar dia is 16 mm, and that is why 600 minus clear cover 20 mm minus 8 mm is the diameter of the stirrup, and minus longitudinal bar dia divided by 2 is 565 mm. So this is basically our effective cover that will be used in the design. So the next part in the manual design of the beam is to determine whether our beam is a singly reinforced beam or a doubly reinforced beam. So as all of you know, we will find it out using MU limiting. So on the right hand side, you can see the snapshot of SP16, page number 10, which gives you the factor of MU limiting divided by FCK BD square. I'll just take the pen. Yeah. So here you can see this is table C of SP16, wherein MU limiting by FCK BD square ratio is given for Fe 500 steel, which is nothing but 0.133. So using that, we will find out our MU limiting for the given beam, which is 0.133 FCK BD square, and the calculation is 0.133 into 30, our concrete grade, width of the beam 300, and our effective depth 565 square. So if you perform this calculation, the MU limiting for our beam is 382 into 10 raised to 6 Newton mm, or you can say 382 kilonewton meter, which is very high as compared to our design bending moment, which is nothing but 90 kilonewton meter. So our MU limiting is very high, and that is why we can conclude that our beam shall be designed as a singly reinforced beam, right? Okay, so moving ahead. Now we know that we have to design our beam as singly reinforced. So then let us calculate another two important parameters, that is the minimum area of steel which is to be provided in an ordinary beam. Now I am stressing ordinary because when I say ordinary, it is basically a beam which will be designed using IS 456, that is for pure gravity loads only. Hence the formula for minimum area of steel in a beam is given in IS 456 2000. You can see the snapshot on the right side. We have added the snapshot in the presentation itself for your ready reference, so that we don't have to go back and forth to the code. And that is why we have intentionally given you the page number as well, so that in case if you want to cross check it, you can open the hard copy of your code or the soft copy and you can get everything validated. And in case if you have any doubt, that will be cleared later on. So coming back, IS 456 2000, page number 46 and 47, the clause is given for requirements of reinforcement for structural members. The member is beam tension reinforcement, and the minimum tension reinforcement is AS divided by BD is equal to 0.85 FY. So if you simply rearrange these terms, we get this formula of AST minimum, which is nothing but 0.85 BD divided by FY. So if we include our design values to it, 0.85, width of the beam 300, effective depth 565, and our steel grade 500, then we land up to the value of AST minimum as 288 mm square. So whatever is our design steel, but we have to provide minimum steel of 288 mm square in the beam. Now, there is one interesting fact to know here, and I have intentionally added this in our slide, because in case if you are using any version of Etabs which is lower than 2015, okay, if you are using any version of Etabs which is lower than 2015, you will find that this 288 will not match up with your AST minimum value. Now, this is a sort of an error in the Etabs design itself, which was removed after the 2015 version. All the versions after 2015 don't have this error. But in case if you are using any version of Etabs which was earlier to 2015, you can go and cross check that your AST minimum of the beam will not match with the IS code formula. The reason being that in the earlier version of Etabs, for this formula, it mistakenly takes the overall depth D in the calculation of AST minimum. So even if you see my Etabs design results, I'll show it to you. The AST minimum value is taken as 306 and not 288, which is actually wrong. Okay. As per code, you can see this is the formula. AS divided by BD is equal to 0.85 divided by FY. The code clearly says that D has to be the effective depth of the beam. But Etabs, unfortunately, the lower version calculates it incorrectly. So friends, whenever you are using Etabs of any version lower than 2015, please take this note that it is giving you wrong value of AST minimum. So as a designer, you have to calculate the correct value using the correct formula and use it in your design. So this was about AST minimum. Now let us go to the next part, which is AST maximum. This is also given to us by IS 456-2000, page number 46 and 47. Maximum tension reinforcement that we can put up in the beam, and its value is 0.04 BD, which is nothing but 4%. Please pardon to my handwriting. Really sorry about it, but okay. So the maximum percentage of steel that we can put in our beam is 4%. And if you calculate the AST based upon it, now, okay, sorry. So if you calculate the AST based upon it, it is 7200 mm square. But the one important thing to note here is capital D. When you are calculating minimum reinforcement, the code is asking you to use effective depth, that is small d. And when you are calculating the maximum reinforcement, the code is asking you to use capital D. So please don't confuse. AST minimum is using effective depth D and AST maximum is using overall depth. So the maximum steel that we can put up in our beam is 7200 mm square. So all these were the constraints of the code, AST minimum and AST maximum. I'll go back to the previous slide. So our actual design bending moment was 90 kilonewton meter. Until now, we have not calculated the reinforcement which is required for this value of 90 kilonewton meter. We have just calculated the minimum area of steel and the maximum area of steel. So now here we will calculate the actual AST that is required for our bending moment of 90 kilonewton meter. Now, since we have extracted the result using our combination of 1.5 dead load plus live load, that means that our bending moment is nothing but a factored bending moment MU. So I am using it straight away, 90 kilonewton meter. There is no need to apply any factor to it because we have already extracted it from Etabs using our load combinations. So MU by BD square. Now what we are doing, I'll tell you first of all. So now in order to calculate the area of steel which is required for our design bending moment, we will use table 4 of SP16, which is on page number 50, to calculate the AST required. Okay, so if you go to page number 50 of SP16, you can find this table which says flexure reinforcement percentage PT for singly reinforced section. Now we have evaluated this at the start itself that we are going to design a singly reinforced beam because our design bending moment is much lesser than the limiting bending moment. So we can use this chart of singly reinforced section. Now this particular chart is given for FCK 30 Newton per mm square. There are charts for other concrete grades as well. Now on the left hand side of the table is the column of mu by bd square, and on the right hand side we have FYS, which is nothing but the yield stress of our steel rebar. So our mu by bd square value comes out to be approximately 0.95. Now what is this mu by bd square? Mu is nothing but your ultimate bending moment, which is factored bending moment. 300 is the width of your beam, and 565 is nothing but the effective depth of your beam. So if you calculate this equation, then we get the value of mu by bd square as approximately 0.95. So if I go to SP16, then for mu by bd square of 0.95, I get the value of my PT as 0.227%. So my percentage of steel required is 0.227%. That is the AST required will be 0.227 divided by 100 into 300 into 565, which is nothing but our small b and small d. So if you perform this calculation, we get our area of steel as 384 mm square. This is nothing but our AST required. Okay. Or you can say that this is the AST that we are going to provide. But previously we have calculated our AST maximum, right? So if I go to the previous slide, just for your reference, our AST maximum is 7200 and AST minimum is 306. So our AST provided is lesser than 7200. I'll just write it down for your reference. Okay, our AST maximum value was 7200. Our AST provided is 384, and the minimum reinforcement that we are supposed to put in the beam is 306. Okay, so 384 is the final AST that we will provide at the center of the beam, as well as at the center of the beam at bottom, as well as at the support at the top. Now I am not performing a separate calculation for the support bending moment and for the midspan bending moment, because our both the values are same, 90 kilonewton meter. Okay, so we have shown the calculation only for one value of 90 kilonewton meter, and our AST is 384. Okay, so I'll just show it to you on the Etabs model, just for your reference, to match that whatever we calculated manually, whether it is matching with our Etabs model or not. Design parameters and everything I have already given to the model, which we will be discussing at the later stage. So I'll just go and run the design directly. The parameters and everything is already given to the models that we will discuss when we go to design in Etabs. All the parameters and preferences will be discussed in detail. Yeah, so as you can see, yeah, this was the beam that we selected for our design calculations. As you can see, the area of steel at the bottom is 387 mm square, and at the support it is 374, 376. There is a minor variation because we have rounded off the bending moment value to 90 kilonewton meter. Otherwise, if you perform the exact calculation, you will get this exact value. So this is the area of steel at the bottom of the beam, 387, and these are the steel at the support, 374 and 376, which are more or less equal to what we got in our manual calculations. And you can see here, this is the AST minimum that Etabs calculate. And since I am using Etabs 2015, it wrongly shows it as 306, right? It should ideally show it as we have seen in the presentation, it should ideally show it as 288. But since it is using overall depth D, it is showing it as 306 mm square. Okay, so this you need to cross check at your end. Okay, so now we are clear that whatever design that we have performed manually, it is exactly matching to what we are getting in the Etabs. Okay. Yeah. So, okay. So this was the part of design of beam for flexure. First of all, we determined whether our beam is singly reinforced or doubly reinforced using MU limiting. Then we found out our AST minimum and AST maximum using IS 456. After that, we found out the actual area of steel required for our design bending moment, again using SP16. And we have also cross-checked it in Etabs that whatever we performed manually, it is exactly matching to what is given in Etabs.
Welcome you all in ISO certified live training program Etabs, RCDC and Excel that makes you a professional structural engineer. In this training program you will learn everything about Etabs and RCDC from basic to advanced, real life project of medium rise structure from architecture plan to final design sheet, real life project of high rise structure with all advanced topics, design of structural elements using advanced Excel sheets. Have a look over the features of this training. Daily live classes conducted by expert for 1.5 hours. Recording of every session with lifetime access. Can interact with expert anytime, 24/7. Exposure to real practice. ISO certification of training completion. It's 5-star rated training program. Till now more than 1,000 participants have benefited from this training program. Now you are the next. Hello everyone, welcome you all in a new ISO certified live training program, design of substructure using CSI Safe, Excel and manual. In this training program you will learn all about the concept of substructure design, commands in CSI Safe software for the substructure design, validation of CSI Safe result with your manual and advanced Excel sheets. This training program will cover 4 real life projects. In the first and second we will cover all the types of isolated foundation in CSI Safe software. In the third real life project we will cover the raft foundation, and in the fourth real life project there will be the coverage of pile and pile cap design of basement wall, and at the end of this training program you will learn how to prepare the final design sheet for the site execution. Have a look over the features of this training. Daily live classes conducted by expert. Recording of every session. Can interact with expert anytime. Exposure to real practice. ISO certification of training. It's 5-star rated training program. Till now more than 1,000 participants have benefited from this training program. Now you are the next.